All right, let's dive into some really cool stuff. We've got these research papers on deep implicit layers, and I'm really curious to see how they kind of twist what we know about neural networks.
Yeah, it's a fascinating shift. You see, usually when we're talking deep learning, we think of these big, explicitly defined structures.
Right, like you've got your input X, and each layer does a very specific thing, like matrix multiplication, add a bias term, throw in a ReLU. It's very step by step.
Exactly. And the problem is, as these networks get deeper and deeper, they become harder to train, they eat up tons of memory, and they might even hit a limit in terms of how well they can represent complex concepts.
So how does implicit layers change all of that?
Well, instead of dictating every single calculation in a layer, we define a goal for the output. It's like saying, hey, here's where we need to end up, but I'm not going to tell you the exact route.
So instead of a function that just spits out the answer, we're setting a condition that the answer needs to satisfy.
Precisely. Think of it this way. An explicit layer is like a vending machine. You put in your money, press a button, and boom, out comes your snack.
Okay.
But implicit layers, they're more like a gourmet restaurant. You tell the chef what you crave, that's your constraint, and they figure out the whole recipe.
I like that analogy, but how do we actually find the output that meets that constraint? Does the network suddenly become a mind reader?
Well, that's where it gets really clever. We can use some powerful mathematical tools to find the solutions we need. Things like fixed point iteration or differential equation solvers, even optimization algorithms. It's a whole new set of tools we can use.
So it's like we're swapping out the engine of a car to be better suited for different terrains. That's pretty neat. And one of the papers even mentions solver agnostic layers. What does that mean?
It means we can define a layer completely separately from how we solve for its output. Think about differential equations for a second. You've got the equation itself that's like your layer, but then you can choose from all sorts of different solvers. Each one might have its strengths and weaknesses depending on the problem.
So modularity is a big advantage here. But let's get into a specific example to see how this implicit thing works in practice.
Sure, let's look at the classic comparison of explicit versus implicit. The research uses the example of scaled self-attention.
The heart of so many modern networks.
Exactly. So the traditional explicit formula takes your input matrices, K, Q, and V, and directly calculates the output Z. It's all laid out step by step, just like a Python function. You'd have Z equals softmax K at QT square IN at V.
I can practically see the code.
Right. Now with implicit layers, we wouldn't define the calculation directly. Instead, we'd set up a constraint that the output Z has to satisfy. It might be something like Z should minimize the difference between some complex function of itself and the input matrices.
So it's like we're shifting from a specific recipe to just describing the desired dish. What are the big benefits of doing this?
Well, this seemingly simple change unlocks some pretty amazing benefits. We've already talked about modularity, but implicit layers can also be way more memory efficient.
Memory efficiency is like a dream come true in deep learning. How does that work?
It all comes down to the implicit function theorem. Basically, this theorem tells us that we can calculate the gradients we need for training right at the solution point without having to remember all the intermediate steps from the solver.
So instead of remembering every single step, the network focuses on the final result. That's got to be huge for those massive models you work with.
Exactly. And this leads us to how we actually solve for these implicit layers. One common method is fixed point iteration. It's beautifully simple. You start with an initial guess, often just zeros, and then you repeatedly apply a function until the output settles down.
Like refining an answer over and over until you hit a stable point.
Exactly. The research uses a great example with the tan function. Imagine an update rule like this. Z equals tan h, wz plus x, where w are your weights and x's is the input. You start with z as all zeros, plug it in, get a new z, and just keep going until it stabilizes.
Okay, so how does that compare to just explicitly defining layers? Is it always better?
Well, there's a trade-off. Fixed point iteration can be way more memory efficient, but it might take many iterations to converge, and sometimes it might not converge at all.
So stability and speed become the challenges.
Right. The researchers actually use MNIS classification as an example. They show that a naive implementation of fixed point iteration can require a huge number of iterations and even become unstable during training.
So fixed point iteration has potential, but it needs some refining.
Yeah, for sure. That's why people are exploring other ways to find the root of these equations. One technique is Newton's method, which tends to converge much faster.
Newton's method. I vaguely remember that from calculus class.
Basically, it's a smarter way to find the roots of an equation. Instead of blindly plugging in values, it uses the derivative of the function to guide the search.
So it's like a more directed search using the slope of the function to get there faster.
Exactly. Now, applying Newton's method to our Ton example involves calculating something called the Jacobian matrix. This contains all the partial derivative. It's basically giving us the directional information we need to quickly find that stable point.
Okay, now we're getting somewhere. But didn't the research mention some problems with implementing Newton's method directly in deep learning frameworks?
You're right. There are a couple of potential pitfalls. First, even though Newton's method is fast, it requires us to calculate and store these Jacobians, and these can get pretty big, leading to memory issues.
Ah, so our memory problems are back.
And there's another subtle issue. Backpropagating through those Jacobian inverses can sometimes be numerically unstable. You can get gradients that explode to infinity or become nan, which basically stops your training dead in its tracks.
That sounds like a pain.
It can be, but that's where the beauty of implicit differentiation comes in.
Okay, now I'm getting intrigued.
It's really cool. Implicit differentiation lets us cleverly bypass the problem of backpropagating through the whole solution process.
You mean we're finding the derivative of the solution implicitly defined by our constraint without worrying about how we actually found that solution?
You got it. And the beauty is this approach works no matter how you solve for the solution. Fixed point iteration, Newton's method, or whatever fancy new algorithm comes along tomorrow. The implicit differentiation formula stays the same.
I'm starting to see how this all ties together. It's pretty elegant.
Right. And it makes implementing implicit layers in our deep learning frameworks much smoother.
Tell me more.
So the research outlines this innate three-step process. First, you solve for the root of your implicit layer, but you do it outside the automatic differentiation tape. That way we avoid those memory problems. Then you engage the automatic differentiation by running just one iteration of your solver, but this time with the solution already in hand. And finally, you add a backward hook, which basically injects the correct gradient information right at the solution point.
So we're using math and clever coding to get these implicit layers working smoothly.
Exactly. It gives us the memory efficiency we want without the instability of backpropagating through complex solvers. It's win-win.
Wow, this has been quite the journey. We've gone from basic deep learning to the nitty-gritty of implicit differentiation and all these clever tricks.
And we're just getting started. Next time, we'll explore deep equilibrium models, DEQs, which take this implicit layer concept to a whole new level.
Welcome back to our deep dive into deep the implicit layers. Last time we really shook things up, exploring the move from explicit to implicit representations.
Yeah, we definitely challenged the way people usually think about neural networks, where everything is carefully laid out step by step.
Right, instead of a detailed recipe, we're just defining the desired outcome and letting the network figure out how to get there. And we saw how implicit differentiation makes it easy to integrate these layers into the tools we already have.
Right, now things are about to get even more mind-bending as we dive into deep equilibrium models, or DEQs. These models take... Oh, hey there, what's up?
So what's the flow-based algorithm?
Oh, you mean the underlying framework we're using?
Good question. You are using PyTorch.
Yeah, PyTorch has great tools for auto-differentiation.
It makes implementing implicit layers much easier.
So are you ready to dive deeper?
I'm ready. Last time, what?
Oh, yeah, uh-huh. Oh, you're asking how flow-based models fit in.
Thanks for the clarification. We can talk about that.
Okay, so flow-based models use neural networks
To transform simple probability distributions,
into more complex ones. It is also related.
they're trained to learn an invertible mapping.
That's another piece of this auto-differentiation puzzle.
Auto-differentiation is how neural networks learn.
Exactly. What did we discuss last time?
Last time we showed implicit layers can be integrated, right?
Exactly. Now things are about to get even more mind-bending as we dive into deep equilibrium models, or DEQs.
These models take the idea of implicit layers to a whole new level.
I'm ready for the challenge. One thing that really got me thinking was the idea of representing an entire deep network as a single equilibrium computation. An entire network in just one layer. How is that even possible?
It's a wild concept, right? It all comes down to fixed points, which we talked about before. Remember how we were repeatedly applying a function until the output stabilized and stopped changing?
Yeah, like with that tan example, z equals tan wz plus x, we kept plugging the output back in until it settled down.
Exactly. So now imagine we extend that idea to the entire network. Instead of individual layers, we have one big function that represents the whole computation. We find its fixed point, the point where the output matches the input, and that becomes the output of the network.
So it's like finding the point where the entire network balances out perfectly.
Precisely. And the amazing thing is, research has shown that this simple shift can capture the power of traditional deep networks, even ones with a theoretically infinite number of layers.
Infinite depth. My brain needs a break.
I know, it's mind-blowing. We obviously don't build infinitely deep networks in practice, but this idea shows just how much representational power DEQs have.
So let's try to unpack this a bit. One of the tables mentioned that a single DEQ layer can represent any traditional deep network. How does that work?
Well, think about how a normal deep network works. You have this series of layers, and each one takes the output from the previous layer as its input. It's like a chain of calculations.
Right, like dominoes falling one after the other.
Exactly. Now imagine we take all the values from each layer and combine them into one giant vector. A DEQ function could take that vector and apply each step of the original network to it, element by element. Finding the fixed point of this function would be the same as running the original network.
So it's like we're compressing this massive network into a single equation. Pretty neat.
Exactly. It's a really powerful theoretical result that shows the potential of DQs.
This is making more sense now, but I have one question. If a single DEQ layer is that powerful, why would we ever stack them? Wouldn't that be redundant?
That's a great question. You're right, stacking DEQ layers doesn't make them more powerful in theory, but there are practical reasons why we might want to stack them. Just like with regular networks, stacking layers can help the model learn better or generalize to new data more effectively.
Okay, so it's not about giving the network more power, but making the learning process smoother and more efficient.
Exactly. Now, of course, we can't just use any random equation for our DEQ function. We have to design it carefully.
Right? There needs to be some thought behind it.
Absolutely. The research suggests taking inspiration from successful cell structures in deep learning.
Like those residual cells that are popular in convolutional networks, the ones with those skip connections.
Those are a perfect example. Residual cells have a structure that helps information flow efficiently and makes training more stable. We can adapt these ideas for DEQs, creating a cell that captures the essence of our network's computations.
So instead of just a simple ton function, we might have a more complex building block with several operations and connections.
Exactly. And the design of this cell has a big impact on how well the DEQ model performs.
It's amazing how we're designing the core of the network, a unit that represents an entire deep architecture. But let's get practical. How do we actually implement these DEQ models?
Good question. The forward pass of a DEQ involves finding the fixed point of our chosen function. We've talked about methods like fixed point iteration, but those can get too slow for complex DQs.
So we need something a bit faster.
Right. One promising technique is called Anderson acceleration. It's a little more sophisticated than fixed point iteration, but it can speed up convergence significantly.
Like fixed point iteration on steroids?
Aha, you could say that. Essentially, Anderson acceleration uses information from previous iterations to make better guesses.
Hi everyone,
as
I'm
it
Zico
searches for the fixed point.
Coulter. I'm with Carnegie
The more
Mellon.
information you have, the better your predictions, right?
Exactly. And the research shows that Anderson acceleration can beat naive fixed point iteration, especially for complex DEQ models.
Okay, Anderson acceleration seems to be the way to go for the forward pass. What about the backward pass? How do we get the gradients we need for training?
That's where our friend implicit differentiation comes in again. Remember that three-step process we talked about?
Solved outside the tape, re-engage, add a backward hook. It's coming back to me.
Exactly. We use the same idea here. First, we find the fixed point using Anderson acceleration, but we do it outside the automatic differentiation tape to save memory. Then we re-engage the tape by running just one iteration of our DEQ function with the solution. We already have it, so it's quick. Finally, we add a backward hook that solves a linear fixed point equation to get the gradients.
So still implicit differentiation, but with a slight twist for DEQs.
Right. The main difference is that the backward pass for DQs involves solving this linear fixed point equation. We can handle that efficiently using Anderson acceleration again or by just inverting a matrix.
Okay, so Anderson acceleration is our go-to for both forward and backward passes in DQs.
It's a powerful tool for sure.
This has been an awesome exploration of DQs. We've covered so much ground from the theory to the practical stuff, but I'm sure there's still a lot more to discover.
Absolutely. DQs are a hot topic in research, and there are still lots of open questions. But before we move on, I want to highlight one important thing. While DQs are efficient and powerful, they do come with some challenges.
Challenges like what?
Well, even with Anderson acceleration, finding those fixed points can still take a lot of computation. And there's no guarantee of stability or convergence, especially for certain DEQ functions.
So while it's promising, it's not a magic bullet for all our deep learning problems.
Exactly. But it's a super fascinating and potentially game-changing area for research.
Welcome back to the final part of our deep dive into deep implicit layers. It's been quite a journey, hasn't it? We've explored fixed points, implicit differentiation, and those mind-boggling deep equilibrium models.
Yeah, we've really ventured off the beaten path of deep learning.
We have, and now we're entering a realm where neural networks don't just compute, they optimize. Get ready to grapple with differentiable optimization.
It's a really cool idea. Imagine a neural network layer that isn't just crunching numbers based on a formula, but actually making decisions based on constraints.
Hold on. So instead of just calculating an output, these layers are actually solving optimization problems. My brain is already in overdrive.
You got it. The output of a differentiable optimization layer is literally the solution to a specific optimization problem that's determined by the layer's input.
Okay, I think I need an example to really get this. Where do we even begin?
Let's start with something, the sigmoid function. That S-shaped curve we use everywhere in neural networks.
Oh yeah, essential for things like probabilities. It squashes values between 0 and 1.
Right. Now, believe it or not, we can actually express the sigmoid function as the solution to an optimization problem. It's essentially finding the value that minimizes a combination of a linear function and a binary entropy term.
Wait, are you saying that the sigmoid function is secretly an optimization problem in disguise?
Exactly. And it's not just the sigmoid. Other nonlinearities like softmax and sparse-max can also be framed as optimization problems. This gives us a whole new way of understanding what these functions are doing and why they work so well.
It's like we're uncovering the hidden logic behind these familiar building blocks. I'm starting to see where this could lead.
It opens up a lot of possibilities. For example, imagine training a neural network where some layers are specifically dedicated to solving optimization problems that are tailored for certain tasks.
So each layer is like a specialized problem solver figuring out the best solution given its constraints.
That's a great way to think about it. And the cool thing is, because these layers are differentiable, we can still use our regular gradient-based methods to train the entire network.
Okay, I'm seeing a power of this, but how do we actually implement these optimization layers? Do we need to somehow embed complex solvers into the network?
That's where it gets really elegant. Luckily, we don't have to start from scratch. There are libraries out there, like CVX layers, that do all the hard work for us.
So we have pre-built differentiable optimization layers. That sounds super convenient.
It is. You define the optimization problem using a simple language, and the library automatically creates the code for a differentiable layer that solves it. But even with these tools, it's good to understand what's going on under the hood.
Absolutely. Can you give us a glimpse behind the scenes? How does the magic happen?
Of course. At their core, these differentiable optimization layers still come down to finding the root of a system of equations. Remember those KKT conditions we briefly talked about before?
Vaguely, there were those conditions that tell us if we found the optimal solution, right?
Exactly. These conditions involve gradients, constraints, and something called dual variables. We can basically treat these conditions as a bunch of equations and then use, you guessed it, implicit differentiation to calculate the gradients we need for backpropagation.
Implicit differentiation saves the day again.
It really does. The research shows how we can express the Jacobian, that matrix of derivatives, in terms of the solutions to the optimization problem.
And with that Jacobian, we can calculate the gradients and training network just like we normally would.
Exactly. It's a really cool combination of optimization theory and deep learning.
This whole deep dive into implicit layers has been amazing. We've gone from fixed points to DEQs to differentiable optimization. It feels like we've barely scratched the surface, though. What are some of the big unanswered questions in this field? What has researchers excited about the future?
Well, one really exciting thing is the potential for DEQs to completely change how we think about network depth. Imagine models that can actually adjust their computational depth on the fly, depending on how complex the input is. This could lead to massive improvements in efficiency and performance.
It's almost like the network is thinking about how much effort to put in, becoming more adaptable.
Exactly. And with these differentiable optimization layers, we're only beginning to see what's possible. Imagine networks that learn to solve complex problems, like planning or decision-making, all within this framework of differentiability. This could revolutionize fields like robotics and AI.
The possibilities are incredible. It's like we're giving neural networks the power to reason and make choices.
That's a great way to put it. There are still challenges, of course, like computational costs and making sure things stay stable. Plus, we need to keep developing the theory. But the future of deep implicit layers is super exciting.
This has been an incredible deep dive into the world of deep implicit layers. Thank you for joining us, and until next time, happy learning.
We've explored so many interesting ideas. I hope you feel inspired to continue learning.